Okay, let's finish talking about section 2.7. And this is absolute value inequalities. So let's start with some basics. Okay, so let's recall this, that the absolute value of x is the distance between x and the origin on a number line. Okay. So if we only have one number line, then the origin is 0. Okay, so here's a number line, here's 0. So, for example, if we were looking at the absolute value of x is equal to 5, then we have two different possibilities. There's a distance to the left of 0, which is 5 units, and that gets us to the number 5. However, there's also a distance to the left of 0 that is 5 units away, and that gets us to the number negative 5. So our solution to this equation would be x is equal to 5 and negative 5. Now, if we had to solve where the absolute value of x being less than 5, well, then on a number line, we would be looking at a region, again, in between negative 5 and positive 5, but now any number in between here would satisfy it. Now, because this is not an equality, 5 and negative 5 itself will not solve it. So now our solution, this is it on the number line, the lowest value goes from negative 5, the highest value goes to positive 5, but in interval notation, this is how we would represent the solution set with parentheses because the endpoints are not included. If we were to write that in set builder notation, it'd be the set of all x such that, well, we put the lower value here, negative 5. X has to be greater than that, or less than 5. It would look different if we were solving the equality, the absolute inequality, where the absolute value of x needs to be greater than or equal to 5. Now, if we were to look at that on the number line, here's negative 5 and 5. Again, we would have two solutions. Okay. If we want the absolute value, or the distance from 0, to be greater or equal to 5, since it's equal, we can fill it in. And then these numbers beyond would be greater than 5. Similarly, numbers less than negative 5 also have a distance away from 0 that is greater than 5. So our interval notation is going to look a little different for this answer. Remember, this is negative infinity and this is positive infinity. So we actually have two sets that we have to represent. So in interval notation, this first interval here goes from negative infinity to negative 5. We can include the 5 because of the equality. And this interval starts at 5 as the lowest value and goes to infinity. Infinity is never included, but this 5 is. And then to say and in set notation, we put a u. Okay? So these are both of our answers. So let's try and solve a more difficult equation with this concept in mind. So for example, if we had the absolute value of x minus 1 is less than or equal to 3. So looking at it on a number line, here's 0, okay. Here's negative 3 and positive 3. Okay. And our solution set will go in between here. Okay. This is what we're looking for. Now, this is not the solution yet, but what's going to get us to 3 on this side is x minus 1 and x minus 1. Okay. If it was just an x, we could say it was 3. X equals 3. Okay. So we really have two different equations here. To find out what x is, it's really that we have x minus 1 has to go in between these two numbers. So it needs to be greater than or equal to negative 3 and less than or equal to positive 3. Because that is what's inside the absolute value. So that's the distance that we're moving. Okay. Alright, now we can just solve this. We'll add 1 to both sides. Or all three sides. Okay. So now x is in the middle. 4 is our upper bound. And negative 2 is the lower bound. Which, if we were to write in interval notation, negative 2 is the lowest value, 4 is the highest value, and they're both included. Let's think about what this would look like graphically. Okay, so this is just our absolute value equation, the parent equation, and we are shifting it to the, let's see, we have to write large. Okay, so we are subtracting, so we're going to the right. So it would look like this. Okay. Remember, this is the basic graph of the absolute value of x. So let's shift it over 1. So now this is the point 1, comma 0. So that's this graph. Okay. And we can ask ourselves, where is that equal to 3? Okay. So the line y equals 3, let's say that's up here. Here's 3. So the line y is equal to 3 goes like this. Now, if we were looking for equality and solutions, we would find them at the intersection points. So let's find out what these intersection points are. That is, when is it that the absolute value of x minus 1 is equal to 3? Well, remember how to solve absolute value inequalities. We can write two equations. It's either that x minus 1 is equal to negative 3 or x minus 1 is equal to positive 3. And then solving this, it's either that x is equal to negative 2 or x is equal to 4. So this would be the point negative 2, comma 3, and this would be the point 4, comma 3. So what that's done is these x values here are what we call critical points, okay? And the graphs behave differently. What we've seen is that this graph is below the line y equals 3, in between negative 2 and 4, which is what we found out up here. This is our solution set. It is below, and therefore it is less than or equal to, it will include these endpoints, 3. But if we look beyond 4, you can see that the graph has gone above y equals 3. And the same if we go below negative 2. So these are not solutions to it. Okay, let's try another one. Let's say we had negative 1/2 times the absolute value of 4x minus 5. We'll add 3 to that. And we want to know where the y values are negative. So if the y values are negative, then we want to know where the function is less than 0. Okay, let's try and solve this. First, let's isolate this absolute value. So subtract 3 from both sides of negative 1/2. Absolute value 4x minus 5. Where is that less than negative 3? And we still don't have the absolute value isolated, so it's being multiplied by this negative 1/2. Let's multiply both sides by a negative 2. It's reciprocal to make that go away. Now these will cancel, become positive 1, and we're left with the absolute value of 4x minus 5. And over here we have positive 6. But we have to remember that we multiplied by a negative. So now we're asking about where is that absolute value greater than 6. Let's find our critical points. Our critical values. Okay. And to do that, we have to solve the equality. So that is, we're solving where is the absolute value of 4x minus 5 equal to 6. And we've done this before, so that means we have two equations. It's either that 4x minus 5 is equal to negative 6, or 4x minus 5 is equal to positive 6. Adding 5 to both sides, we'll get 4x is equal to negative 1. And dividing by 4, x is equal to negative 1/4. So this is one critical value. Here, adding 5, we'll have 4x's is equal to 11. And dividing by 4, x is equal to 11 over 4. So these are our critical values. So these values will split up the number line into 3 different intervals. Here's negative 1/4. Here's 11/4. And so we're wondering about what's going to happen with the graph in each of these intervals. That is, will this graph be above 0 or below? This is not easy for us to sketch a graph of. The good news is, though, is that once we determine how the graph will act in each of these intervals, it will be the same for all values in that interval. So what that means is we can just pick text points. Because the graph will act the same on that entire interval, we just have to pick any value that's easy to work with. So for example, in this interval, I would certainly pick 0. It's very easy to deal with a 0. Okay. So if this was 12 over 4, this would be the number 2. So 2's in here. That's not too bad to work with. We could also work with 10. It doesn't matter. I usually default to negative 10, 0, and 10. It doesn't matter. Okay, it's up to you. All right. Now we have to evaluate each of our test points. Okay. So test each and put it into the original inequality. Okay, so we're going to pick negative 10. So is negative 1/2 4 times, and we're picking, our test point is negative 10. So we'll substitute in negative 10. or whatever value you've decided that's in that interval, and at plus 3, and then we're going to ask ourselves, is that less than or equal to 0? So now we can just evaluate. This is negative 1/2 times, well, this is negative 40 minus 5 is negative 45 plus 3, is that less than 0? It's negative 1/2. Well, the absolute value of negative 45 is positive 45 plus 3. Is that less than 0? Perhaps you can see from right here that it's not. Okay. This is negative 45 halves plus, well, 3 is just getting a common denominator, is 6 halves. Oh, I'm sorry, it is. Negative 45 halves plus 6 halves is negative 39 halves. And that is less than 0. Okay, so it is true on this interval. Sorry about that, it is true on that interval. Okay, so what does that mean for us? That means on this interval, it is true. And so I like to just draw that in. It's true here. Okay. Now let's try 0. Okay. So at 0, we'll plug it in, negative 1/2 times the absolute value plus 3, and is that less than 0? Okay. And we're plugging in 0. Okay. So now this becomes negative 1/2. Simplifying inside of here, 0 minus 5 is minus 5 plus 3. Now the absolute value of negative 5 is positive 5. That has to be multiplied by negative 1/2. We'll add 3. That's the same as negative 5 halves. And again, we'll get a common denominator for 3. Adding 3 is the same thing as adding 6 halves. And negative 5 halves plus 6 halves is 1/2. And 1/2 is not less than 0. So this is false. So I come back to this page, and on this interval it's false. Now let's test this interval. In 10, again, just rewriting to test it out. I'm going to substitute in 10 there, or whatever value you decided. Okay? And we're going to ask ourselves, is that less than 0? And we picked 10. Okay. So again, simplifying, negative 1/2 times the absolute value. 40 minus 5 is 35. We're adding 3. The absolute value of 35 is 35. That has to be multiplied by negative 1/2. Then we will add 3. This is a negative 35 halves. And again, we'll write 3 as 6 over 2. So this is equal to, okay, so negative 35 plus 5 would be negative 30, plus 1 more is negative 29 over 2. Okay. And this is less than 0, so this is true. Okay. So that means over here I can come back to my little sketch, so I'm understanding now. It's true on this interval. Now I go back and I look at the original to determine if the endpoints are going to be included. Okay. So the original does not have an equality, so we're only looking, so they will not be included. Our solutions are only going to be from here to here. So this is how we represent our solutions on the number line. To do it in interval notation, remember this is negative infinity. So our first interval goes from negative infinity to negative 1/4, and 1/4 is not included. Then, and we'll union it with this interval, and the lowest value here is 11/4, and it's not included. And the highest value is infinity. So this is our solution set in interval notation. So let me show you what that looks like graphically. So here is the negative 1/2 graph. Okay. We were asking about where it's less than 0. So to be less than 0 means the graph lives below the x-axis, and that does that for values of x from negative 1/4 to all the way out to negative infinity. Or again here it's 12.75. I think I said, what did I say? 12 divided by 4 was 2. It's not, it's 3. So 3 would be the value that we pick in the interval. If we pick 2, clearly it's in that interval. So I apologize for that. So graphically, that's what we're talking about. All right, let's try another one with the absolute value. Negative 2 times the absolute value of x minus 4, where is that less than or equal to negative 6? Okay. So again, we're going to have to isolate the absolute value. And right now it's being multiplied by this negative 2, so let's divide by negative 2. Then those will cancel. And on this side we have the absolute value of x minus 4. On this side, the negative and negative become positive, and 2 goes into 6 3 times. But we're dividing by a negative, so don't forget to flip the sign. Then we just follow the process. I need to find critical values. So to do that, we need to solve the equality. So we need to solve the absolute value of x minus 4 is equal to 3. So the absolute value of x minus 4 then will either be equal to negative 3, or x minus 4 will be equal to positive 3. Adding 4 to both sides, we have that x is equal to 1, or x is equal to 7. These are our critical values. That means they will break up the number line into 3 different intervals. And we need to pick test points in each of these intervals. So a number that's in this interval is 0. 0 is very easy. We can pick anything in here. Say 5, why not? Okay. And 10's out here. So these are our test points. And now we have to evaluate them. Okay. So we'll put them back into the original. Let's see here. The first one we're looking at is 0. So is it that negative 2 times the absolute value is less than or equal to negative 6? And we're putting in 0. And then we just crunch away. This is negative 2 times the absolute value of negative 4. Is that less than or equal to negative 6? Well, the absolute value of negative 4 is positive 4. That's being multiplied by negative 2. Is that less than or equal to negative 6? And it is true, negative 8 is less than or equal to negative 6. So it is true. Okay. So I come back over here and make a note to myself that this is true. Okay. Now we're going to test in this interval. So to do that, we'll use 5. So this becomes negative 2 times 5 minus 4 is 1. Now the absolute value of 1 is 1. That's multiplied by negative 2. Negative 2 times 1 is negative 2. And negative 2, we're looking at, is that less than or equal to negative 6? This is not true, so it is false on this interval. And now I can make note of that in here. And we only have one interval left to test, and to do that we'll use 10. Okay, here we go. Negative 10. I'm sorry, positive 10. So negative 2 times the absolute value 4. Okay. Is that less than or equal to negative 6? That's what we're asking. So I put in 10. This becomes negative 2 times the absolute value of 6. This is negative 2. The absolute value of positive 6 is positive 6. So this side is negative 12. And is negative 12 less than or equal to negative 6? Sure. So that's true. So I come back to this side, and I'll make a note over here that it's true on this interval. So I know I'm looking at intervals like this. Oops, from here. And now I have to decide if the endpoints are included. So to do that, I go back to the original. And the original does include the equalities. So these endpoints will be included. And now I have to write the answers in interval notation, remembering this is negative infinity, and it goes all the way up to 1, and it does include 1. Then union with this interval. This interval starts at 7, and 7 is included, and it goes up to positive infinity. Okay, so this is a methodology that we need to, you might want to put it on a flashcard so you understand the process. But if we know this process, then we can solve all sorts of other inequalities. So, for example, we have, let's do a quadratic. So let's say we have to solve where x squared minus x is less than 6. So step 1 in the methodology is we're going to look for critical values. And to do that, we solve the equality. So we need to solve x squared minus x is equal to 6. Well, this is just quadratic. We can solve that. It's often helpful when solving quadratics to have them equal to 0. We'll hope then that they factor. That would be our quickest methodology. And this one will factor into x minus 3 and x plus 2. Minus 3 plus 2 is minus 1. Okay. And then solving this, we know that either x minus 3 equals 0 or x plus 2 equals 0. So it's either that x is equal to 3 or x is equal to negative 2. And these are our critical values. So the next thing we do is put those critical values on the number line. So now we've created 3 intervals for us to test. Okay. The next step is to pick your critical values, or your test points. Okay. So in between here is 0. That's easy enough. Out here, let's say 10. And down here, negative 10 is in there. Okay. And now let's start this. Okay. For negative 10, we'll put this back into the original. Is negative 10 squared minus a negative 10? Okay. When we're done, we'll ask if this is less than or equal to 6. Okay. Now, negative 10 squared is positive 100. Okay. And remember that subtracting a negative is going to turn it positive. So this is plus 10. And I hope it's clear then that this is false. 110 is not less than 6. So we'll write false there. Okay. We can pick 0. Is it that 0 squared minus 0, is that less than 6? Well, sure, 0 is less than 6. Okay, so this is true. And then lastly, let's test this interval, sorry. Is 10 squared minus 10, is that less than 6? Well, 10 squared is 100, minus 10, and sure. No. 100 minus 10 is 90, and 90 is not less than 6, so this is false. Okay, and now I'm just steps away from being finished. We just need to write our answer in interval notation. Okay. So it's going to be true in between these 2 values. Okay. And we'll double check if we're going to keep these endpoints or not. So I come back to the original. On the original does not have that little equal to sign. So these 2 endpoints will not be included. So our answer starts at negative 2. It is not included. And goes all the way up to 3, which is not included. This methodology will also help us solve rational functions. We do have to extend our definition of critical values. So say, for example, okay, so critical values. That is number 1, where the function is equal to 0, or the other thing that breaks up a number line is if the function is undefined. Because at that point we'll get asymptotes. Okay, so let's look at 1 over x plus 3. Let's add 2 to it, and let's find out where this is greater than 0. Okay, so first thing we need is our critical values. So number 1, that's where the function is equal to 0. So let's solve where 1 over x plus 3 plus 2 equals 0. Well, let's subtract 2 from both sides. To get 1 over x plus 3 is equal to negative 2. And you can think about this as negative 2 over 1 if you'd like. let's clear this fraction because our x is in the denominator and we can't have that. So let's multiply both sides by x plus 3. You can think about that as x plus 3 over 1 if you'd like. Now these will cancel, and we're left with 1 is equal to, and let's distribute this, negative 2x minus 6. And now this is just a simple linear equation. I can add 6 to both sides to get 7 is equal to negative 2x, or that x is equal to negative 7 halves by dividing through by 2, negative 2. Okay, so this is one critical value. This one critical value comes from when the function is equal to 0. Okay? But since this is rational, we have to worry about the other definition of critical values and find out when it is that the function is undefined. Okay. Well, the function will go undefined if this denominator ever equals 0. So we know that x plus 3 cannot equal 0, so x cannot equal negative 3. So these are our two critical values. Once you have the critical values, the next step is to write down your number line. Okay. And let's see here. Negative 7 halves, that's negative 3.5. Yeah, because negative 3.5. So it's not very big. Okay. So let's say here's negative 3, and here's negative 3.5. Okay. Now we're going to have to pick test values, hopefully the easiest ones we can get. So I want 0 and negative 10. And so I guess we could look at negative 3.25, right? So that would be negative 3 1/4. Which is 12, negative 13, 12 over 4. I don't know which of these forms it'll be easier for us to work in. 3 1/4. 3 times 4 is 12 is minus 3. Okay, so we'll have to see as we're evaluating which ones become possible here for us. So let's think about, before we do this, what the shape of this graph might be. Okay. Let's do some translations. Okay. So 1 over x plus 3 plus 2. Okay. If this is our function, okay, what's going to happen is that this is our parent function is 1 over x. Okay. And the parent function looks like this. It has horizontal and vertical asymptotes. This one's x equals 0. This is y equals 0. And the graph stays bounded like this. Okay, this is our parent function. So how is this graph these translations going to affect it? Well, this x plus 3, I'm going to the left, so I'm adding. So I'm going left 3 units. And then this will move it up 2. So let's just sketch a graph of that. Okay. So if we had to sketch a graph of that, okay, if I move this graph to the left 3 units, every point has to come left, okay, including that vertical asymptote. Okay, so now this vertical asymptote is not the line x equals 0, but now it's line x equals negative 3. The horizontal asymptote would just stay the same, and if I was just translating it, the graph would look like so. Okay, this would just be f of x is equal to 1 over x plus 3. But we have to deal with this translation now of shifting everything up 2 units. So if I shift everything up 2 units, the horizontal asymptote must also go up 2 units. So now instead of the equation being y equals 0, it's y equals 2. Shifting the vertical asymptote up and down doesn't do anything as far as moving its position. Okay, so it's x equals -3. And now the graph should look like so. At a certain point in time, there will be an x-intercept here. And we know what that's at. That is when this function, here's our critical value, we set it equal to 0, and this was when x is equal to -7/2. So we know this is -7/2, comma 0. And now we go back to the original equation. Why was sketching this helpful for us? Okay, so this is a sketch of what the graph should look like, and we are concerned about where is this function greater than 0. Okay. Now we could use our test points. I was just looking in here, okay, but I thought I might do a sketch to help me get a better idea. Well, if I want the graph to be greater than or equal to 0, it needs to be above the x-axis. Okay? So it is greater than 0 on this side, okay, because it's above. Now, on the other side of the x-intercept, it's below 0. And then on the other side of x equal to -3, the graph is above 0 and will stay there because of its horizontal asymptote at y equals 2. So graphically, we have determined that the solution set will go from -infinity up till that 7/2, -7/2. And looking back at the equation, the endpoints will not be included. So I will not include 7/2. And then unioned, again, on this side, now from 3 to infinity. Okay. So graphically we know this is what the solution set should be. Okay. But that's all. We only know that because we knew how to do the translations. If we don't know the translations, let's plug and chug with these numbers and put them in and verify that. Okay. So at -10, let's plug it in, find out if that's greater than 0. Okay, so -10. So this becomes 1 over -7 plus 2. Is that greater than 0? Okay. I'm going to move this negative up top so we don't lose it. And then we could write 2 as 14 over 7. And so is it true that 13 over 7 is greater than 0? Yes. It is positive. So it is true on this interval. Now let's pick what's going to be easier. I think it's going to be easier if we use, okay, so we had talked about -3.25. Well, we can put that in. All right, let's see. So this is -3.25, and then I'm going to add 3 to that in the denominator. And then we add 2 to it. And we're going to figure out if this is greater than 0. Okay. So now, this will become -3.25 plus 3 is -0.25 plus 2. Is that greater than 0? Now, to solve this, we know that negative, let's convert it to a fraction. Okay. We know that negative 0.25 is negative 1/4. And we'll add 2. Okay. And now, when you're dividing with fractions, it's the same thing as multiplying by the reciprocal. Okay. So this is negative 4 plus 2, which is equal to negative 2. And negative 2 is not greater than 0. So it is false. And that's what we saw graphically. In between here and here, the graph is below 0. Okay, so it was false on that interval. And one last one to verify this, because we might not always be able to sketch the graph so easily. And this one we had picked 0. So 1 over 0 plus 3 plus 2, is that greater than 0? And so this is 1/3 plus 2, is that greater than 0? And sure, a positive number adding to a positive number is greater than 0. So it's true. Okay. So it's true on this interval. I forgot to write down that it was false on this interval. Okay. And then we go back to the original. Let's see. So we know it's going to be here to here, here to here. And then we go back to the original to determine about if these endpoints are included. And there's not a little line under there saying or equal to. So in this case, these stay open. And we have shown algebraically, that is, we put the pencil to the paper and did some algebra. We've shown that the solution set has 2 intervals, which are these. Okay. And these intervals agree with the intervals we have down here. And the way we did it down here was that we solved it graphically. Okay. Let's construct the absolute value of x. Okay, so let's say we have a number line. Let's pick 5. Okay. And let's say we wanted to know now about numbers that were a distance of 4 units away. Okay. Well, I might be concerned in both directions. Okay. And I think it's pretty easy to see then. We can just do some math here that 5 plus 4 would be 9. And 5 minus 4 would be 1. So any value in between here would solve this, or satisfy this equation. Okay. Now, what does that look like as far as an absolute value is concerned? Well, we set up the absolute value, and we were centered around 5. Okay. The unknown is x. And we want that distance now to fall in between here, so this would be less than or equal to 4. Okay. So what that means is that this absolute value inequality is equivalent, meaning the same, as the interval notation of saying that x can go from 1 to 9 included. I just wanted to make this distinction. So we could then we could describe all x values within a distance of 3 from 2. Okay? So if we want to do that without having to write all those words down, let's set up a number line so we can understand the situation. Okay? Okay, from 2, excuse me, is my start point. Okay? So from 2, I want to know all values, a distance of 3. Okay, so I'm going to go here to here is 3, and also in this direction is 3. So 2 plus 3 is 5. 2 minus 3 is negative 1. Now, they've said within, so now I know that within this distance falls here. So I could write this as this all x values, so we'll put in x, from our starting point, which is, we started at 2. Okay. We want that to be less than or within. So within means less than or equal to, and the distance was 3. So if they'd said without or outside of, then we would be talking about numbers outside of here, and we would want this distance to be greater than or equal to. Okay, so that is a lot of information that's very important for you to know. So email me if you have questions.